All right, welcome back. We are on chapter 12 and we're looking at solutions. And we've done a lot of calculations involving solutions now. And so we're going to do a couple more things just talking about what happens when you have a solution to its temperature, its boiling point, freezing point, and vapor pressure. So those are kind of some of the terms we're going to be looking at. But I have to start with a question. So here's a question I want you to think about. All right, what happens to something when you heat it? All right, so you're heating it. What's going on? Is it going to get warmer, colder? Nothing happens and it depends. Those are your four options here. I'll let you think a second. All right, so most of you probably are thinking and you're saying, well, if you're heating something, it should be getting warmer. And that's what I would say too, right? It's getting warmer because you're heating it, but it depends, okay? So the correct answer would be D, it depends, and you're like, well, what does it depend on? So we're going to be looking at water, okay? And if we start with ice and we start heating it, what's going on to the molecules involved, and what's going on with the temperature to the solid ice, and then to liquid and to the gas as we heat it. So this is called a heating curve, and this is for water. You can get a heating curve for other substances as well, but we're going to be looking at water. We're going to start when it's really cold, okay, in the ice phase. And as you heat it, the molecules in the ice are going to have a little bit more energy. They're going to get a little bit warmer as you heat them. So on the bottom here, on the X, we have heat added. And then on the Y, we have the temperature in degrees Celsius. So that's the temperature of the water. As you're adding heat, let's look what happens. So initially, we're starting with ice, okay? And as you go up, okay, the temperature of the ice is going to warm from -20, where we started, to 0 degrees Celsius. Now, when we get to this temperature, and now 0 degrees Celsius should stick in your head, right? Because that is the freezing point or freezing temperature if you have pure water. You keep adding heat, all right? What happens then? And you can see our line now has, the slope has gone to 0 here. We've kind of made a straight line across. Even though we're adding more heat, the temperature of the water is not changing. Why is that? Well, before we were adding heat and the temperature was changing, we were increasing the kinetic energy. At this point now, we're not increasing kinetic energy, we're going through a phase change. And so all of the ice is melting at this point. All right, so at this point from -20 to 0, we have now started that phase change when we hit 0 degrees. Now after all the ice has melted, you continue to add heat, the temperature of the water, now we're in the liquid phase, will continue to rise. Again, now we're increasing the kinetic energy and the temperature goes up until we hit the next phase change, all right, at 100 degrees Celsius. And at this temperature, you keep adding heat, but the temperature of that water is going to remain constant at 100. All right, why is that? At this point, all of the liquid water is turning into vapor. So this is that phase change again. And at these phase changes, okay, you can keep adding heat. The temperature does not change because all of that heat added is going through that phase. What's going on in that phase? Okay, and you can see that the phase where it stays 0, okay, is not as big as compared to where it stays at 100. Seems a little bit bigger. At that point, you have to break intermolecular forces to get through that phase change, all right? So from a solid to a liquid, about 15% of the hydrogen bonds have to be broken for water to go through that phase change. And then you have to break all of the remaining hydrogen bonds to go from the liquid to the gas phase. All right, so you can see how that one takes a lot more heat to get there. All right, and then as you continue, once you have gone through that phase change, now all of the liquid has gone to a vapor, you can continue to heat the vapor and the temperature will go up. All right, so this is the heating curve for water. You should be able to explain what's going on when you're heating it, okay, and when you're not at the phase change and when you are at the phase change. A couple other things. This is for pure solutions, okay? We can talk about the normal boiling point. And that just means that there's nothing added, and the normal boiling point also is when it's at 1 atmosphere. So at normal atmospheric pressure. For water, we know that's 100 degrees Celsius is the boiling point, and the freezing point's at 0. So a couple things to pay attention to there. We're going to be looking at what it means if you do not have a pure solution. All right, so what happens if you add something to water? How would that change this heating curve? Would it change the temperature that the water turns into ice, or the temperature that the water would boil? We'll be looking at those properties in the next couple videos. All right, so we're going to be looking a little bit with vapor pressure. And we have to kind of explain what we mean by this. So vapor pressure is the pressure exerted by gas molecules of a liquid. So we kind of are talking about it in the liquid phase, but it's the gas molecules that are doing some reaction. And these are when the liquid and the gas states are in a dynamic equilibrium. All right, we're going to get to a whole chapter on this word equilibrium, but we can represent this by these double arrows right here. What this means is that the reaction rates are not changing. We have liquid water, some of it going and making gas, okay, so this is vapor, and then some of that can kind of condense back and go back to the liquid phase. When the rates aren't changes, this is when we're in an equilibrium. Let's see, a couple other things here. We just talked about that. The rate of the forward reaction is equal to the rate of the reverse reaction. All right, we have to look at what this means for the vapor pressure though, okay? So even when you are below the boiling point, okay, so the boiling point for pure water is 100 degrees Celsius, even below that, some of the molecules of water will still have enough energy, not all of them, but some have enough energy to kind of leave the liquid phase and go into the gas phase. All right, so we call that the urge to evaporate. All right, and why would they have the urge to evaporate? Okay, so vapor pressure, I'm just going to write this out. Liquids have the urge to evaporate. And one of the reasons this would be is because if they go from the liquid to the gas phase, this is an increase in entropy. Which we talked about in the previous lecture, that systems tend to go in a way that will increase entropy or increase the randomization or distribution of energy in a system. All right, so vapor pressure then will increase, if you can see this, with temperature. So here is the vapor pressure, it's in millimeters of mercury, and here is the temperature. We can see that as the temperature goes up, okay, so from 0 all the way to 105, what happens to the vapor pressure? Vapor pressure is also increasing. All right, so if you have a cup of water, let's say, and you just let it sit out for a while, even though you're not increasing the temperature of the water, it's at room temperature, over time, that water would evaporate due to the fact that it has that urge to go from the liquid to the gas phase. Let's just quick look at this little picture here. This is from the Russo textbook. They are trying to show that if you put some water into a closed container, and then in this closed container you took out, okay, so it's in a vacuum, you took out all of the air, so there's no air pressure there. So all you have is water. All of a sudden, over time, okay, this water is going to enter in dynamic equilibrium between liquid and some gas molecules. So some of these water molecules will escape out, and at this is 23.76, so we can say this is going to be at 25 degrees Celsius. There's a vapor pressure of 23.76 millimeters of mercury. Now if you increase the temperature of this water, we could see this value going up as well. All right, I think that should be covering it. Let's talk a little bit more about vapor pressure and relating it to boiling point. All right, so like we just were saying, the higher the vapor pressure, the greater the tendency for liquid molecules to escape into the gas phase. Okay, so if you have a high vapor pressure, more of the molecules will have more energy in order to go from a liquid to a gas. Let's look at this picture down below. There are 3 different beakers, and all of them, okay, there's these dueling arrows, if you can see that. All of them have an arrow pointing down, and this is due to the atmospheric pressure. And at sea level, the atmospheric pressure is 1 atmosphere, which is 760 millimeters of mercury. So they all have the same vapor pressure. Now, you can see that the temperature is related to the vapor pressure. And as you increase the temperature, the vapor pressure goes up. So here's the beaker at 25 degrees, 70 degrees, and then 100 degrees Celsius. All right, so at 25 degrees, there's a little bit of a vapor pressure, okay, because the molecules don't have as much energy, but some of them are still able to escape into the gas phase. As you increase in temperature, there's a more urge for those the molecules in the liquid to now escape to the gas phase. And when you get to 100 degrees, what do you notice about the vapor pressure and how it compares to the pressure coming down? We now have equal pressures, all right? And when the vapor pressure equals the atmospheric pressure, this is called your boiling point. All right, so the battle of the dueling arrows, when they are equal to each other, this is your boiling point. All right, so when does boiling occur? Boiling occurs when the vapor pressure equals the external pressure. All right, couple things then to note. And the next question it brings up an interesting point. What will happen to the boiling point if you are in the mountains in Denver? So if you've been to Denver, you know that the air, people will say, oh, the air is thinner. You have less pressure. The atmospheric pressure is decreased, okay? So instead of being around 1 atmosphere is normal, when you're up in the mountains, the vapor pressure, or I'm sorry, the atmospheric pressure, the pressure atmosphere, I would say is around 630. Kind of varies with weather and stuff, but let's just say 630 millimeters of mercury. That is the messiest I have seen my handwriting for a little while. Let's just get this fixed up a little bit. Pressure, atmosphere in the mountains, 630 millimeters mercury. All right, so if your pressure is lower, okay, so here they are all 760. Let's draw another flask, and this time, instead of being 760, this is now only 630. So that means that your vapor pressure only needs to get to 630 to get to the boiling point. Well, it won't need as much heat put in then, so you're going to actually now boil at a lower temperature. All right, so let's think about how this would affect, let's say, if you're making mac and cheese. All right, so you have to boil your pasta, okay, at sea level, at 1 atmosphere. I think Kraft mac and cheese is like 7.5 minutes of boiling, okay? You probably have made mac and cheese before. All right, so you have to boil it for 7.5 minutes. That's expecting that you're getting it to a temperature of 100 degrees. Well, now if you have a lower pressure, atmospheric pressure, the vapor pressure only needs to get to that lower pressure before you start boiling. So instead of boiling at 100 degrees Celsius, you're boiling less than that. So what you would have to do then would be to increase the time that you are boiling so it gets the pasta all the way cooked. Now, if you're hungry and you don't want to wait longer, okay, what's one thing that you can do that you probably know about? If you read any of the instructions for cooking things at a different altitude, okay, so there's higher altitude cooking, one thing you can do is either cook it longer or you can increase the pressure, so use some type of pressure cooker, okay, so if you increase the pressure, now you're not cooking at 100, but you might be cooking or boiling at a temperature higher than that. Or you could add something, okay? Sometimes it says you can add salt to the solution, and that will change something. We're going to get into what it does, but it will change the temperature. So instead of the current boiling point, you can get it to boil a little bit higher temperature to get it to cook better. All right, we'll look at more to what that salt does in the next video. So stick with me. Here we go.